All right, so we're going to talk about graphing square root functions, but to start off, what we're going to do is we're going to talk about transformations and identifying the vertex, okay? So this works very similarly to absolute value functions as well as vertex form for quadratics, all right? So just like in the other two that we just mentioned, when we identify our vertex, the x value is going to switch its sign, okay? So this is going to become a -3, whereas the y value is going to be the same, okay? If we remember vertex form, it's very similar for square root functions. So it's square root of, or a times the square root of x minus h, on the outside plus k, and our vertex is h comma k. All right, so notice how the sign, because it's the subtraction sign in the formula, it ends up switching, which is why the x is going to change each time. The domain and range are going to come directly from this vertex, all right? It'll make a little more sense when we do our graphs in just a second, but we can say that x is going to be greater than or equal to -3, because that's the first point, and then our y is greater than or equal to -2, okay? I would also say that this has a vertical stretch. That 3 being multiplied by it, or our a value, is going to cause it to be a stretch. If it were negative, it would be a reflection. If it were a fraction or in between 0 and 1, it would be a shrink. And because we have either a translation on the x or the y, that does cause it to be a translation. So I want you to go ahead and do all of page 1, identifying the vertex, domain and range, as well as the transformations. And then, so you can pause the video. I have an answer key on the front table that you can check, but then you can resume the video after you checked your answers, so we can do the 3 graphs on page 2A. All right, so pause the video. And welcome back. Okay, so now we're going to go ahead and graph a couple square root functions. We're going to start with the parent function. So here we go. The parent function is y is equal to the square root of x. So we could just plug in values all willy-nilly, but we're not going to do that, okay? We do have a process. So we're always going to start with the vertex, okay, using the method we just done from the previous page. So in this one, we realize that there's no transformation on the x. It's just going to be 0, and nothing on the y. So our vertex here is 0, 0, okay? This is going to be the first point that you graph. It's also going to be the end point on the shape that we'll graph, which you'll see in a second. All right. The next thing we're going to do is we're going to use something called the 1-3-5 rule. Okay. What we do is we're adding 1 and then 3 and then 5 on our subsequent x values. What this is going to do is this is going to make it so that the x value that you plug into your square root is going to be a perfect square, okay, and make it the problem a lot nicer. So let's go ahead and try it out. So we already did x value of 0. We're going to add 1, so it would be 1. Add 3 to that, which would be 4, and add another 5 to that, which would be 9. Okay, so now we can go ahead and plug these x values in to get our y values. So if we plug in 1, the square root of 1 is 1. If we plug in a 4, the square root of 4 is 2. And the square root of 9 is 3. So you notice those came out as nice integer values. This will be even more helpful when it's less obvious what those values will have to be to plug in. So it'll be more clear even in our next problem. So let's go ahead and graph this. So we have 0, 0. We have 1, 1. We have 4, 2. 1, 2, 3, 4, 2. And then we have 9, 3. So 1, 2, 3, 4, 5, 6, 7, 9, 3. Okay? So you'll see we have this shape that kind of looks like a half parabola. Okay, so it's just going to be this positive arm. So you'll notice that vertex right there is the end point, that starting point of that shape. We can go ahead and do our domain and range. So in this case, once again, the domain and range refer to that vertex. Okay, it refers to this point. So if we're referring to x values, we're saying it starts at 0 and goes up, so it's greater than or equal to 0. And the y values do the same thing, starting at 0, going up. Okay, so that'd be our domain and range. All right, let's go ahead and take a look at the next one. This is problem number 2. All right, same kind of thing. Right now we can look at this already. You should be able to know what kind of transformation is taking place. We should know this is a vertical shrink. We should find our vertex right away, which is once again 0, 0. Okay, and then we can use the 1, 3, 5 rule to figure out which x values will result in perfect squares under our radical. So in this case, we add 1, it's 1 again. 3 gets us 4, and 5 gets us 9. So once again, no changes here because our vertex was once again 0, 0. Our next example will see something different. So we can go ahead and plug these in. Plug in a 1. The square root of 1 is 1 times a half gets us a half. Plug in a 4. The square root of 4 is 2 times a half will get us 1. And then 9, the square root of that is 3 times a half will be 3 halves. Okay, and we can graph it. 0, 0, 1 and a half. It's going to be hard to see on my graph. 4 is 1, 2, 3, 4, 1, and then 5, 6, 7, 8, 9, and that's 1 and a half. So you'll see that shrink. Oh, it's a sloppy graph. But you'll see the shrink taking place. On your paper, it should be a little bit more clear. My graph is just pretty small. And once again, the domain is exactly the same, and the range, because our vertex did not change. All right, last one. This one will have the most to do. All right, for number 3. So right here, we can identify there's quite a bit of transformations. We have 2 different translations taking place. We also have a vertical stretch. All right, so let's start by finding our vertex, okay? X changes, so this is going to be a positive 2, and this is just stays the same, which is a 1. So our vertex is 2, 1. We can even graph it. 1, 2, comma 1. All right, cool. So now we're going to use that 1, 3, 5 rule. This is where it really takes effect and actually helps out to make sure we result in perfect squares underneath our radical. So we don't have to deal with irrational numbers. So 2 plus 1 is 3, 3 plus 3 is 6, and 6 plus 5 is 11. All right, let's give it a shot. So if we plug in the 3 here, 3 minus 2 is 1. The square root of 1, 1. So 2 times 1 plus 1, which will get us a total of 3. Okay, we can graph 3, 3. 2, 6. If we plug in a 6 here, we have 6 minus 2, which is 4. The square root of 4 is 2. So 2 times 2 is 4, plus 1 is 5. So 6 comma 5. 1, 2, 3, 4, 5, 6, 5. And then last one we'll do is 11. So if we plugged in 11 here, 11 minus 2 is 9. The square root of 9 is 3. 2 times 3 is 6, plus 1 is 7. So we can plug that in. So this was 6. So we can do 7, 8, 9, 10, 11, and 2 more. And you'll start to notice that we always go 1 over, 3 over, and 5 over, just like the 1, 3, 5 rule shows. And the amount that you're rising here is your A value. So that's something I can get us closer using a trick in graphing this. But we can go ahead and do the domain and range once again. X is greater than 2 or equal to, and y is greater than or equal to 1. All right, so there are our 3 graphs. Let's do one final thing. We're going to recap what we should do, and then we'll be done. Okay, so to recap, 1, always start by finding the vertex first. 2, use the 1, 3, 5 rule to choose x values that will result in perfect squares underneath your radical, or your square root. And then 3, plug in the x values to find your y values and graph it. That is essentially all you need to know. So at this point, I would like you to turn your page over and work on 2b, graphing it as well as naming the transformations, vertex, and domain and range.